The main double angle formulas are sine 2a, formulas for sine 2a, cosine 2a, and tangent 2a. And they can be derived easily from the sine a plus b formulas, but you just call it sine a plus a. So this one becomes sine a cosine a plus cosine a sine a. And because these are actually equivalent to each other, it becomes 2 sine a cosine a. That's our sine 2a formula. Cosine 2a formula is a little bit unusual because there's actually going to be 3 variations on it. The first one is cosine a minus sine a sine a, which turns into cosine squared a minus sine squared a. This is version number 1, and it's actually the least popular version. Because if I replace this sine squared with 1 minus cosine squared, it turns into cosine squared a minus parentheses 1 minus cosine squared a, which turns into positive 2 cosine squared theta minus 1. I'll call it a. That's a more popular version because it only involves one thing instead of this one that involves cosine and sine. If, on the other hand, I go back to version 1 and replace the cosine with 1 minus sine squared, I get 1 minus sine squared a minus sine squared a turns into 1 minus 2 sine squared a. And these versions 2 and 3 are the more commonly used ones because each one involves just one piece, either cosine or sine. And tan a, if you just replace b with a in the tan a plus b formula, becomes 2 tan a, that's tan a plus tan a, over 1 minus tan squared a. And those are our 5 formulas, one for sine 2a, one for tan 2a, and 3 different versions for cosine 2a, but really this number 1, even though it's where the other 2 come from, it's not used that much. So an example of a question they do is if sine a is given to you as 2/3 and they tell us where a is between 0 and 90 degrees, sine 2a is 2 sine a. Cosine a is 2 times 2/3. For cosine a, I like to say cosine a is the square root of 1 minus sine a squared is 1 minus 4/9 is square root of 5 over 3. So the answer becomes 4 root 5 over 9. So for sine 2a, since it has both sine and cosine, we're going to have to do extra work to get that. The best kinds of questions are ones like this. We're being told something, and we're being asked for cosine of 2a, because here we have a choice, and of the 3 formulas, I'm going to use the one that has only cosine in it, 2 cosine squared minus 1, 2 cosine squared a minus 1, which is 2 times 1/4 squared minus 1, which is 2 over 16 minus 1, which is 1/8 minus 1, which is negative 7/8. So if I just know cosine, I can get cosine 2a pretty easily. And even if I just know sine, sine a equals 3/4. I'm just keeping a between 0 and 90. If it's not, you may have to, well, for this one, since we want to know what cosine of 2a is anyway, we're going to use the version 1 minus 2 sine squared a is 1 minus 2 times 3/4 squared is 1 minus 2 times 9 over 16. That's 1 minus 9 over 8, which is negative 1/8. So that's the way these formulas work. The only time where we have to do some extra work is if tan a is given and they want to know what cosine of 2a is. I need either sine or cosine. I'm going to use 2 cosine squared a minus 1. But since tan a is given, a sneaky trick you can do here, you just pretend that a is an acute angle, and tan is the opposite over the adjacent, and then the hypotenuse is 5. So cosine of a is going to be 4/5, and it's going to be positive because a was an acute angle. So this is 2 times 4/5 squared minus 1 is 2 times 16 over 25 minus 1 is 32 over 25 minus 1 is 7 over 25. Now there are some nice proofs without words for these. This one picture has a circle with diameter 2 and a bunch of things sort of drawn in here. And from this picture, we can see that if this angle here is 2 theta, this angle out here would have to be theta. There's a rule that an inscribed angle is always half of the central angle if they intercept the same arc. So that would make this angle have to be half as that. So if the radius is 1, this piece from here to here would be cosine of 2 theta, and this piece here would be sine of 2 theta. Now this is kind of sneaky here. We've been focusing on this little triangle, but there's also this bigger green triangle. And there's also this big red triangle. Now this red triangle is interesting. It's a right triangle because any triangle inscribed in a semicircle is a right triangle. And its diameter, its hypotenuse is 2 because it's the diameter of the circle. So if this is theta here, the adjacent is r, this adjacent is r cosine theta, and that's why it's 2 cosine theta. That's this piece right here is 2 cosine theta. Now let's say I didn't know that this piece was sine 2 theta already. Then if I wanted to analyze this piece right here, I could say that in this blue triangle here, I have angle theta with hypotenuse 2 cosine theta. So this side would be hypotenuse times sine theta, or 2 cosine theta to sine theta. But we already had from another analysis that it was sine 2 theta, and that gives us this identity. Now for the other one, I'm going to erase. For the other one, see this here, this is 2 cosine, so cosine 2 theta plus 1. That's how long that line segment is. This is cosine 2 theta, this is 1. But on the other hand, if I didn't know that, and I instead was just looking at this blue triangle, I would say that that blue triangle has a hypotenuse of cosine theta, 2 cosine theta. But since this red is like the adjacent side, it's going to be r times cosine theta, so it's going to be 2 cosine theta times cosine theta, which becomes 2 cosine squared theta, and if I just subtract 1 from both sides, I get the cosine of 2 theta identity. This is a very similar picture with similar proof. And this one's real interesting. We have a rectangle with a diagonal of 2, and if this is theta, this is 2 cosine theta. It's hypotenuse times cosine theta. This is 2 sine theta. So the area of this triangle is 2 sine theta cosine theta, 1/2 base times height. On the other hand, this other triangle has to have the same area up here. But if I look at that triangle and I draw in this I'm going to treat this 2 as the base, and then the height is going to be this line. Well, confusing thing here, but this angle here is going to equal 2 theta because it's the it's exterior angle to a triangle, to this triangle here. This is the exterior angle, so it's the sum of the two remote interior angles. So, and this little red triangle has hypotenuse of 1, so that the opposite side is sine 2 theta. So the area of this triangle here, if I go 1/2 base, I call the base is going to be 2. So 1/2 of 2, and the height is sine 2 theta, and the 2's cancel out, and we get sine 2 theta equals 2 sine theta cosine theta. There are other proofs also, but I think this is good. I want to keep this video at 10 minutes.